Welcome back, friends. Now that you have looked at designing pedestrian facilities at your urban streets, let us now focus on the other type of non-motorized transport, which is designing for cycling or bicycling infrastructure. So, in this lecture, we will be looking at the different principles, just as we had several principles of NMT infrastructure that we had looked at. Now, we will specifically look at principles for designing bicycle infrastructure and also look at some of the cross sectional design elements. These are all based on IRC 11, which was released in 2015. So, in designing for bicycle facilities, we have to again keep in mind that we are not only dealing with bicycles, we are also dealing with rickshaws, cycle carts, hand pulled carts, etc. So, there are different types of vehicles or non-motorized bicycles that we are dealing with. Not only the ones that are adult touring, but they may be luggage attached to it, that kind of a bicycle. There may be a cycle rickshaw that we are talking about, maybe cycle carts and hand pulled carts. So, all of this combined together forms the design principles for cyclists. And then it is also, the design is also based on which type of road we are designing it for. The hierarchy of the roads in the transportation network matters in this case, whether it is an arterial, subarterial, whether it is a local street. So, it matters on which street we are designing the bicycle network. The 5 basic principles to keep in mind while designing for cycle infrastructure is coherence, directness, safety and security, attractiveness and comfort. Right? Many of these are very similar to what we had looked at it when we were trying to design, or when we were designing pedestrian infrastructure, where they had to be safe, secure, they had to be attractive, or they had to attract the people, choice users to using this facility. They have to be comfortable, it has to be direct, should avoid detours and so on and so forth. Right? And the other thing that IRC recommends is that we design facilities so that a speed of at least of anywhere between 5 to 15 kilometer per hour can be maintained on such facilities. Right? If it is too low, then the bicyclist will be discouraged from using such facilities, and if it is too high, then there might be some safety repercussions for bicyclists. We will you have already maybe looked at such bicycle lanes which are also now available in few cities in India. Bicycle boxes are something that are coming up, which allows you to which allow the bicycles to come up to the front and right next to the in the front of the intersection, so that when the signal turns green, the bicyclists are the first people who can leave the intersection safely. And you must have also encountered some public bicycle sharing systems in your cities, which allow you to not own a bicycle, but still use the bicycle by renting them at an hourly basis, and the rents are usually very cheap. So, as per the IRC guidelines, there are some standard dimensions for different types of bicycles. IRC defines 4 different types of bicycles. First one is an adult touring bicycle, second one is an adult touring bicycle with goods, next one is a rickshaw, and next one is the last one is a goods rickshaw. So, it defines 4 different classes of bicycles, and for each class of bicycle, it has some standard clearances and widths. So, if you just look at one of them, you would say that the first one, capital W, is the width of the cycle itself. So, when we look at the width of the cycle for different classes of cycle, it ranges from anywhere between 750 millimeters to about 1.4 meters. So, that is the range of the width of a cycle. The next one, small a, is the clearance from obstacles which are very close to the bicycle. anywhere between 0 to 50 millimeters away. So, this is A, right. So, you have to have no obstacles where your pedal, essentially where your pedaling zone is, right. If your pedaling zone, if you have any obstacles, then you will not be able to pedal very smoothly. So, that is what A tells, what A represents. B is the clearance zone from obstacles anywhere beyond 50 mm, but less than 150 mm. So, that is B. Okay. So, anywhere between beyond 50 mm, but less than 150 mm. C is clearance from fixed obstacles like poles and bollards. So, you have to have your poles and bollards at least a few millimeters away from the bicycles. So, again, like you remember, bicyclists usually prefer to ride on the edge of the roads. So, as you ride closer and closer to the edge of the road, many of the street furniture also comes very close to you, but a safe design is to have a basic clearance from your street furniture or fixed obstacles like poles and bollards, and D is the final clearance is D, which is clearance from any kind of closed walls, right. So, all these values of A, B, C and D and for different types of cycles are shown in this chart. These are again based on IRC 11/2015. The next element in designing for bicycle infrastructure or cycling infrastructure along urban streets is to look at the turning radius of the bicycle track or the shared use path or whichever you are trying to design. Bends, they should be smooth connections between cycling paths and ensure continuity, right. These bends that you are often trying to design, they depend upon the turning radius. You would be coming at a certain speed and would be wanting to continue at the same speed, but bends always restrict the speed by a certain amount. So, by how much amount should they be restricting, so on and so forth, depends upon the turning radius that you provide. Sharper the bend, the lower will be the speed, the more sharp you provide, but it is recommended that the minimum design speed of 12 kilometers per hour be maintained at all bends, right. If a cyclist traveling at 12 kilometers per hour comes at a bend, he or she should be able to negotiate the bend at that speed. So, it is preferred that a turning radius of 30 meter or more is provided, which also ensures that visual directness and continuity of the path is maintained. So, this person should be after negotiating the bend should be able to visually see, and also the path would be continuous. Radius of less than 10 meters should not be considered, as it does not permit cycling at a comfortable cruising speed, right. So, these are some principles you have to keep in mind while you are designing for turning radius of a bicycle. So, if you look at the turning radius and its basic physics principles, what happens is the weight of the bicycle plus rider is coming downwards. There is some sort of a friction with the road. So, that friction is given by a coefficient of friction times W, which is nothing but mg. So, Fs times mg is the friction. So, the radius at the turn, if you provide r, and if the bicycle speed is v. So, the reaction to the ground has two components, this r has two components, r cos theta and r sin theta. R cos theta counterbalances the weight, right. R cos theta counterbalances the weight, whereas r sin theta and the friction acts as the centripetal force for which the bicycle turns. So, r sin theta is nothing but m squared mv squared by r plus your friction, which we already know as Fs time mg. So, if you divide 2 by 1, tan theta is equal to, you would get. So, if you divide equation 2 by equation 1, you will get tan theta is equal to v squared by rg plus Fs, or if you solve for v, you will realize that the maximum speed at a bend that a cyclist can maintain depends upon the radius that is provided at that bend, right, and there should be sufficient friction that allows the bicyclist to negotiate that bend and ensures that he or she does not skid at that bend. So, a maximum is the maximum speed at which the bicycle can turn without skidding. So, V max is the maximum speed, and that is given by the square root of r times g times tan theta minus f s. So, IRC 11 suggests that the f s value should be 0.3, coefficient of friction of 0.3, theta should not be more than 18 degrees. So, people should not be bending for more than 18 degrees, and a widening of about 0.51 meter per lane is required to accommodate the extra width on account of this bending. So, at the bend the cycle track is widened by at least 0.51 meters in order to accommodate for that speed. Okay. In case of bicycle lanes, usually super elevation is not necessary, just as opposed to when you are providing for a turning radii for motorized vehicles, super elevation may be required, but in this cases super elevation is not required. So, if you look at a quick problem, then you would understand how to determine the maximum speed. So, if you are asked to determine the maximum speed which is required for a bicycle to make a safe turn without skidding for a turning radius of 30 meters, utilizing all the information given in IRC 11. So, all the information meaning all these values, right. So, if you use all this, also you have to comment if this speed is good for operation and discuss a way for its improvement. So, let us see what is the result of this maximum speed based on 30 meter turning radius. So, you know already the formula for it. If IRC suggests a Fs value of 0.3 and a theta of 18 degrees, and you have you already know that the turning radius is 30 meters. Turning radius is 30 meters and g is 9.8. This should be 30 meters and g is 9.81. So, if you putting these values, you will get a maximum speed of 21.17 meter per second. So, in your comments and discussion section, what you can write is cruising speed of a bicycle is usually anywhere between 18 to 20 kilometers per hour. Remember, when we were, if you go back a few slides, we had told you that at least anywhere between 5 to 15 speed is required, and also minimum design speed at bends should be at least 12 kilometers per hour. So, here what we are seeing is that for negotiating anywhere between 15 to 20 kilometers per hour and maintaining this speed of 15 kilometers, the radius that should be provided, if you use the same formula and find out the radius for maintaining a 15 kilometer per hour speed, you will see that such a high radius usually is required, 922 meters of radius. Such large turning radius may not be available at urban roads. So, usually such large turning radius is not available, hence the speed at the bends should be lowered a little bit while you are approaching a bend. So, that is the discussion that you have to have, right. Now, the next thing, design element to remember is when you encounter any inclines or slopes. So, it is very as it involves a lot of physical activity in bicycling, usually bicyclists do not like to have very steep inclines or slopes. So, they should be the most desirable consideration is to avoid any level changes, but if level changes have to be made, there are some standards that are provided by IRC. If the level to be negotiated is only about 1 meter, then the recommended slope is anywhere between 1:12 and 1:20. Whereas, if a railway overbridge, for example, has to be negotiated, then the slopes become anywhere between 1:40 to 1:60. Negotiating a bridge and a tunnel may be unavoidable for cyclists, so that becomes a problem, but if the slopes are if the recommended slopes are implemented, it helps the bicyclists negotiate those negotiate such a rough or a steep incline. Very important to make the ground level more cycle friendly than expecting cyclists to detour from their natural path. So, as much as possible we have to keep a level floor, or the level has to be kept as low as level as possible. Otherwise, the cyclist will have to take a detour, which means a longer distance, and if the distance keeps on increasing between the origin and destination, then bicyclists would not want to use the mode of transportation or this NMT mode of transportation and go back to using their motorized vehicles. So, we want to avoid any such situation. And also on a decline, junctions and obstructions should be spaced reasonably far from the bottom of the incline, because cyclists need plenty of free space at the bottom the incline to recover the speed. So, usually what you will see is that when you are coming down, people usually do not recommend a speed hump right at the bottom of the incline, but a speed hump usually a little bit later on, so that there is some recovery time given to the bicyclists. And also, next thing to remember for the cross sectional elements is, because we had told you earlier that the design depends upon the type of road, you have to keep in mind for which type of road you are developing your design for the bicycle facility. It depends upon the hierarchy of the road. So, if you look at 4 different hierarchies: arterial, subarterial, collector and access roads, you will see that usually the right of ways of such roads are given here 50 to 80 meters for arterials, whereas for access roads the right of way is very less, anywhere between 6 to 15 meters, and the design speed of vehicles is given here. So, when you know the design speed of vehicular traffic, it becomes very essential to design your bicycle tracks according to such design speeds. Otherwise, they may become too unsafe for the cyclists to use their cycle on any one type of roadways. If you look at the cross sections of each of these, you would see that in any type of arterial or subarterial road, you may have a service road, right? You may have a service road or a service lane, which may or may not be used for parking. Then you may have your brown area, which may be a footpath, right? Then you have your orange cycle tracks, you may have a cycle track after the footpath, and then you may have a tree belt which separates the cycle tracks from the actual carriageway, right. So, you may have this type of a design, whereas the alternate designs are very close to each other. In this type of design, you may have the tree belt or the swell on the left hand side rather than on the right hand side, and you may only have a very small vegetation that separates the bicycles with the vehicles on the main carriageway. On the other hand, you may have a tree line on the extreme left hand side, even the left of the service lane, and you may have your sidewalks, cycle lanes and a little bit of vegetation between the carriageway and the bicyclist. So, different cross sections of roads shown for either arterial or subarterial type of categories of roads, for which you can develop your or design for your cycle tracks, right. more or less you see that the cycle track and the footpath are always most likely to be next to each other. Apart from in the last section where you see that there is no when there is no service lane, at that point everything is at the left hand side of the road. The other prototype is a collector or a distributor street. In a collector cross section, you can see that usually you do not have any service lanes. Usually you can at that point in time put your design your cycle tracks on the carriageway itself, because right next to the carriageway itself, because what happens is the speeds along collectors or distributor streets, the average speed of vehicles is low. So, the cyclists feel safer to ride along with the motorized vehicles when compared to arterials or subarterials, where the average speed of the traffic is very high. So, they need always a separation from the traffic, right. So, that is the basic difference between when you are designing a cycle track for a collector or a distributor street versus when you are designing it for a arterial or a subarterial street. Again, you can go through each one of the different prototypes in this case. Sorry. Finally, when you are looking at a local street or an access street, it is very similar to the situation that you encounter in the previous collector or distributor street, where the average speed of vehicles on the right of on the carriageway is pretty low. So, you may not even have a different cycle lane, right. So, you see there is no different yellow marking cycle lanes. The cyclists and the motorists can coexist on the same carriageway, because the speeds are pretty low. So, you can have a then the vegetation path between the cyclist and the pedestrians, or you can have the pedestrians right next to the bicyclists, or you can sometimes, which is case in our Indian cities, many of our Indian access streets or local streets, whereas there is no sidewalk for the pedestrians as well, as they are walking on the same carriageway as the bicyclists and the motorists. This is okay when it is the it is an access road or access street or a local street, because the average speed of vehicles is low. Similar type of prototypes are shown for more access and local streets. Finally, when you start looking at some of the dimensions and some of the measurements for different types of bicycle infrastructure. So, the different types of bicycle infrastructure include segregated cycle tracks, cycle lanes, or if they are riding with the motorized vehicles, right. They can be any type of this. So, if the number of lanes or an arterial is anywhere between 6 to 8 lanes divided, and maximum width of the car lane is 3 to 3.3 meter, it is always recommended that there be a segregated cycle track. So, if you are on an arterial with a maximum of 6 to 8 lanes divided, and each of the car lane widths are 3 to 3.3 meters, at such situations it is always recommended that you have a segregated cycle track. Usually means that the average speeds of the vehicles are very high. So, the cyclists feel unsafe riding with the traffic or with the vehicular traffic, and hence they need a segregated cycle track. Similar is the case for subarterials, when you have about 4 to 6 lanes divided and a car lane of 3 to 3.3 meter, you have to have a segregated cycle track. But you see, as you start getting more local and local from a point of view of a distributor or a collector street and a local or an access street, where there are only 2 lanes or maybe even 1 lane of width of 2.75 to 3 meter, they can ride with the mixed traffic, or they can just have a cycle lane. This lane can be designed on the carriageway itself, and they need not have a segregated cycle track. So, as the hierarchy of the roads decrease, hierarchy decreasing meaning average speed of vehicles on the roads decrease, your need for a segregated separate cycle track also reduces, right. Cyclists become more and more comfortable riding with the traffic. So, they can ride with mixed traffic. Similarly, if you look at other design elements such as gradient and the width of lanes required. If you are on an arterial which has a gradient of 1:12 to 1:20 and the lane width, desirable lane width of such a minimum of 2.2 meter for 2 lane track and 3 to 4 meter for shared lanes of segregated cycle tracks need to be provided. So, you also have to remember how much wide cycle tracks you need when in case of different types of gradient that are available at different hierarchy of roads, right. So, when you are on a distributor, you just need a cycle lane, you can have a 1.2 meter painted cycle lane. When you are on an access road, you do not even need a lane, because they are going to ride with the mixed traffic. So, I hope you have clearly understood how to design for different types of bicycle facilities based on the different roadways on which these facilities are to be provided. That brings us to the end of this lecture series. We have looked at end of this lecture. We have one more lecture left in this series for this week. In this lecture, we have taken references from the IRC 11 which was developed in 2015, and some of the cross sectional pictures have been taken from the planning and design guideline for cycle infrastructure developed by the Shakti Sustainable Energy Foundation. You have been exposed to what are the different design principles for designing bicycle facilities. You have been exposed to how the bends at different cycling tracks have to be provided, and what is the minimum cycling speed that has to be maintained, and also how different cycling infrastructure has to be designed for different hierarchy of roads. Thank you very much.